Good afternoon, students.
Good afternoon, ma'am.
Good afternoon.
Okay, have you had your lunch today?
Yes, ma'am.
Okay. Those who are facing any kind of network issues, then no problem. Others are, please switch on your videos. Okay. Okay, Lakshmi. Okay, children. So in our last class, we discussed about the Newton's first law of motion. And the Newton's first law of motion is also known as law of inertia. And we are already discussed what is the relation between mass and inertia. So first of all, we can recollect all these points once again. After that, we can move to the Newton's second law of motion. So starting with Anandida, tell me the Newton's first law of motion.
An object remains in a state of rest or in a uniform motion in a straight line unless it is compelled to change the state of that state by applied force.
Yes, very good. An object remains in a state of rest or state of uniform motion in a straight line until or unless it is compelled to change that state by applying an external force. This is what is known as the Newton's first law of motion. Lakshmi Nandakumar, can you say any two applications of Newton's first law of motion? Any two applications? Lakshmi, switch on your video. Same question to Nandana. Any two applications of Newton's first law of motion?
Ma'am, when a bed sheet is flicked away and suddenly dust particles fall away as they tend to.
Yes, whenever the bed sheet is flicked, the dust particles are flies away from the bed sheet. It is because of the Newton's first law of motion. Can you explain this with the help of law? How it is occurs? Yes, Lynette. Lynette is ready to help you. Yes.
And when the bed sheet is flicked, the bed sheet is in motion, but the dust particles is in rest. So when suddenly it is flicked, the bed sheet is flicked, the dust particles is in rest, and they will go in opposite direction where the bed sheet is flicked.
Yes. So initially the dust particles are in rest positions. So inside this bed sheet, the dust particles or bed sheet or in carpet, we can explain the same thing in the case of carpet. The dust particles are initially in the state of rest. Okay. So according to our Newton's first law of motion, when an external force is applied onto this bed sheet or into this carpet, what happens? The dust particles are compelled to change their state of rest into state of motion. That is why when we are flick the bed sheet or when we are flick the carpet, the dust particles which is initially in the state of rest are compelled to change that state of rest into motion. Okay, good. Then Amarjit, tell me one more application for Newton's first law of motion.
Ma'am, when we are traveling in a car.
Yes?
Ma'am, when we are traveling in a car.
Okay, when we are traveling in a car or bus, how you can explain this phenomenon with the help of Newton's first law of motion?
When the driver suddenly brakes.
Okay, whenever the driver suddenly brakes, what happens to the position of the object?
Move forward.
Yes, we move forward. So suppose if the car is in a uniform motion or the bus is in a uniform motion, we are in a stationary position. But suddenly, whenever the driver applies the brake, that is an external force is acting on that car, what happens? The object which is initially in the rest position compelled to change that state. So that is why the object or that person leans forward or becomes pushed to in a forward direction. Okay, so these are the applications of Newton's first law of motion. Newton's first law of motion is also known as law of inertia. Then Sridev, tell me what you mean by inertia.
The tendency of an object to stay in the rest position.
Or Always in a rest position or in uniform motion. The tendency of an object to remain in a state of rest or in a uniform motion. That tendency of an object is known as inertia. Okay, that tendency possessed by the object is known as inertia. Okay, then Nigila Mary, what is the relation between inertia and mass of an object? Relation between inertia and mass of an object. Nikila? No idea. Atleo, what is the relation between inertia and mass of an object? Unmute and say, what is the relation between inertia and mass of an object?
Mass is the amount of matter present in a.
Yes, mass is used to measure the inertia. Okay, and what is the relation between them?
No idea.
Is it directly proportional or indirectly proportional?
Directly proportional.
Directly proportional. So mass is a physical quantity. Mass means the amount of matter that contained in an object is known as mass. So the relation between mass and inertia is that mass is directly proportional to inertia. What do you mean by the term directly proportional? If one quantity increases, the other quantity is also automatically increases. So if the mass of the object increases, what happens to the value of inertia, students?
It increases.
It also increases. If mass of the object is decreases, what happens to inertia possessed by that object?
It decreases.
It also will be decreases. So suppose if I will give you two samples, one is a feather and other is a truck. One is a feather and other is a truck. Which one possesses greater inertia?
The truck possesses greater inertia.
Yes, the truck possesses the greater inertia. Why the truck possesses greater inertia?
It has mass, greater
Yes,
mass.
because it possesses greater mass. If the object possesses greater mass, then we can say that that object possesses greater inertia, because mass and inertia are directly proportional to each other. Is it clear?
Yes, ma'am.
Okay, can we move to the next topic?
Yes, ma'am.
So the next topic is Newton's second law of motion. Newton's second law of motion. So students, before entering into the Newton's second law of motion, first we should know about a term called momentum. Have you heard about momentum?
Yes, ma'am.
Then can you define what you mean by momentum? I think
It's about the movement of an object.
it's about the movement of an object. Okay, so first of all, let us see what you mean by momentum. After that, we can explain the Newton's second law of motion. So all of you write the heading momentum. So the next topic, momentum. So if you get an idea about the momentum, then only we can easily describe and state the Newton's second law of motion. So the next physical quantity or the new term that we are going to study is momentum. So here, first of all, I will show an image. So here in this image, you can see the two cars. What is the difference between these two cars?
One is a
One
toy.
is one
Yes.
is small, one is large.
Okay, one is small and one is large, or we can say one is a toy car. It is a toy car and other is a real car.
Original.
Okay. One is a toy car and other is a real car. What about the mass between or mass of these two cars? Which one possesses greater mass?
The original car.
Yes, the real car. The original car possesses the greater mass as compared to that of the toy car, right? So these two cars are in motion. You just imagine this real car and toy car are in motion. So to which of these cars we need to apply a greater force in order to stop its motion?
The real car.
Yes, it is to the real car. So out of these two cars, we need to apply a greater force to the real car in order to stop its motion because it possesses a greater mass. So we can say that the force required to stop an object is directly proportional to its mass, right? So here from this observation, we can say that the force required to stop a moving body is directly proportional to its mass. This is the first conclusion that we are drawn from the first figure. That is, if greater the mass, greater will be the force that we needed to stop that moving body. Is it clear?
Yes, ma'am.
Okay. So now I will show another image. Suppose you just imagine the two cars. Both are real cars. They're having the same mass, but they are moving with a different velocities. Suppose here it is traveling with 400 km per hour. This is traveling with a velocity or speed of 1000 km per hour. Okay. So what do you think? To which of these cars, to which car I need to apply a greater force in order to stop its motion?
A car with velocity 400 kilometers.
Yes, the second one. Is it with 400 kilometer or with 1000 kilometer? Yes, some of them are set for 400. So here we need to apply the force, greater force onto the second car because it is moving with a greater velocity. So what is the conclusion that we are drawn from this figure? The force required to stop a moving body is directly proportional to its velocity, right? Because the first car is traveling with a velocity, both of them having the same mass. Suppose if it is possess a 150, not 150 or 1000 tons and all. For example, the first car possesses a 450 kilogram weight. Second car also possesses a 450 kilogram. The mass of the two cars is the same, but they are traveling with a different velocity. The first car is traveling with a velocity of 400 km per hour, but the second car is traveling with 1000 km per hour. So from this, we can say that we need to apply a greater force on the second car in order to stop its motion because it possesses greater velocity. So the conclusion that we are drawn from this figure is force needed to stop the motion of an object is directly proportional to, from the second case, the force required to stop a moving body is directly proportional to its velocity. So from the first figure, we drawn the conclusion that force required to stop a moving body is directly proportional to its mass. If greater the mass, greater will be the force that we need to apply that moving object in order to stop that moving object. From the second figure, we drawn the conclusion that if greater the velocity, greater force will be needed to apply on that moving object in order to stop its motion. Okay. So from these two observations, here it is clear that there is a quantity of motion. That is directly proportional to mass and velocity. Or we can say that from these two observations, there is a quantity of motion that depends on mass and velocity of a moving object. That quantity of motion is known as momentum. Okay, so there will be a quantity of motion that depends upon the mass and velocity of a moving body. That quantity of motion is known as momentum. So here we are going to see the definition for momentum. Momentum is the product of mass into velocity. So what do you mean by momentum? It is the product of mass into velocity. Momentum is the quantity of motion in a body and it depends on its mass and velocity. All of you write the definition for momentum. Momentum is the quantity of motion in a body. It is a quantity of motion of a body that depends on mass and velocity. So there is some particular quantity is there, particular quantity of motion is there that depends on mass and velocity of that moving object. That quantity of motion is known as momentum. And this is the definition for momentum. Momentum of a body is defined as the product of mass and velocity. You only need to study this definition. Momentum of a moving body or momentum of a body is defined as the product of mass and its velocity. Product of mass and velocity. Mathematically, we can write momentum is equal to mass into, because here it is the product of mass and velocity. Product means multiplication, mass into velocity. Momentum is equal to mass into velocity. Momentum is represented by the letter P. So P is equal to M into V. P is equal to M into V. So what is the definition for momentum? Yes, what do you mean by momentum? Adikesh?
Momentum of a body is defined as the product of its mass and velocity.
Yes, very good. It is the product of mass and velocity. Alan, mathematical equation for calculating momentum?
Momentum is equal to mass into velocity.
Mass into velocity. Then who is here? Hira. How we can represent it in letter form? Which is the letter used to represent momentum?
Ma'am, P.
P. P is equal to?
P is equal to M into V.
Yes, P is equal to M into V. So here we define the term momentum. Momentum is, we should know about the momentum, then only we can define the Newton's second law of motion. So here momentum is equal to momentum. Momentum is equal to mass into velocity. Momentum is equal to mass into velocity. And the letter that is used to represent the momentum is P. It is not by M. Here P is used to represent momentum. P is equal to, M is represented by, mass is represented by M and velocity by V. So P is equal to M into V. This is the mathematical equation for calculating the momentum. So now we can write an equation, not equation. Now we can derive an SI unit for calculating the momentum. What is the SI unit of mass? SI unit of mass?
Kilogram.
Kilogram. Kg. Kilogram. SI unit of velocity?
Meter per second or
Meter.
kilometer per hour.
Velocity, meter per second. SI unit. SI unit is?
Meter
Per second. Not kilometer per hour. It is meter per second. So SI unit of velocity is meter per second. SI unit of mass is kilogram. So the SI unit of momentum is kilogram meter per second. SI unit of momentum is kilogram meter per second. SI unit of momentum is kilogram meter per second. So here we study a new physical quantity, that is momentum. Momentum is the product of mass and velocity. Okay, you just kept the equation in your mind. P is equal to mv. where P is the momentum, M is the mass, V is the velocity, and its SI unit is P is kilogram meter per second. SI unit of momentum is kilogram meter per second. Is it clear?
Yes, ma'am.
Okay, then Ken, can you define what you mean by momentum?
Momentum is the quantity of motion in a body and it depends on its mass and velocity.
Okay, it depends on its mass and velocity. And Tom Jones, mathematical equation for calculating momentum?
Mass into velocity.
Tamanna, SI unit for momentum? SI unit. Amin, SI unit for momentum?
Ma'am, P.
SI unit. P is the representation for momentum. SI unit. Who can say the SI unit for momentum?
kg
Ma'am, kg.
Kilogram meter per second. Kilogram meter per second. Okay. So here we can write some characteristics of this momentum. The momentum is directly proportional to mass. Momentum is directly proportional to mass. Here one example is given. If a cricket ball and a tennis ball move with the same velocity, momentum of cricket ball is more because its mass is larger than that of the tennis ball. So here instead of this cricket ball and tennis ball, we compare a real car and a toy car. So when we are comparing a real car and a toy car, the real car possesses greater momentum. Why?
Because it has more mass.
It has larger mass.
Yes, because it has larger mass or it possesses greater mass. Similarly, here they will give another example in the case of cricket ball and a tennis ball. If you are consider a cricket ball and a tennis ball possesses greater momentum because it possesses larger mass as compared to that of the tennis ball. The second one, momentum is directly proportional to velocity. Momentum is directly proportional to velocity. So instead of a tennis ball, suppose if we are consider the two cricket ball with the same mass, but they are moving with a different velocity, then we can say that if we are consider the two cricket balls with the same mass and with a different velocity, then the momentum of the cricket ball with a greater velocity possesses greater momentum. Momentum will be greater for the cricket ball that is moving with a larger velocity. Now again, we know that the momentum can be calculated by the equation T is equal to mv, right? P is equal to the product of mass into velocity is known as the momentum. Suppose you imagine if a body is at rest. Okay, if the body is at rest, what is the velocity possessed by that body?
0.
0, because it is not in motion. So the velocity possessed by the body is equal to 0. So we know that momentum can be calculated by P is equal to mv. If the body is at rest, what happens? If the body is at rest, the velocity of that body is equal to 0. So we have P is equal to m into 0, which implies P is equal to 0. That is, if the object is at rest, the momentum possessed by that object at rest will be equal to 0. Or in simpler words, you can say you can write, for a stationary object, the momentum P equal to 0. For a stationary object means object at rest. They are not, that object is not in motion. So for a stationary object, the momentum P is equal to 0. But every moving object possesses a momentum. Every moving body possesses a momentum. But if the body is at rest, it doesn't possess any kind of momentum. It will be equal to 0. Another characteristics of momentum, it is a vector quantity. Momentum is a vector quantity. What did you mean by this statement?
Thus both
Possess
magnitude.
direction and magnitude.
Yes, very good. Because it possesses both magnitude and direction. Momentum possesses both magnitude and direction. So momentum is a vector quantity. And the last point we are already discussed here. SI unit of momentum is kilogram meter per second. It is kilogram meter per second. Or we can write, this method is also right, kilogram ms raised to -1. Both are representing kilogram meter per second. The SI unit of momentum is kilogram meter per second, or the same unit we can represent in the manner kg ms raised to -1. Both method are right. Both are representing the SI unit of momentum. You don't need to write the CGS system because in nowadays we are following the SI system of unit. The CGS system of units are used in earlier days. So nowadays we are using this, follow this SI system of units. So it is not important. The CGS unit of momentum is not important. SI unit of momentum is kilogram meter per second, or the same thing we can represent it like this, kilogram ms raised to -1. Is it clear?
Yes, ma'am.
Okay. So now I hope that all of you get an idea about the momentum. So we can move to the Newton's second law of motion. Newton's second law of motion. All of you write the next heading. Newton's second law of motion. So here we have the Newton's second law of motion. So the Newton's second law of motion is based on this momentum. That is why we consider the term momentum first. So what is Newton's second law of motion states? The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction of the force. Direction of the force. Direction of the force in which it is acts. You just make it a symbol and it is takes place in the direction of the force. That's all. So this is what is our Newton's second law of motion states. According to our Newton's second law, the rate of change of momentum. It is not simply the momentum. Rate of change of momentum is directly proportional to the applied force. That is the force acting on the object. And that force takes place, and the direction of the force takes place in the applied direction. Okay, the rate of change of momentum of a body is directly proportional to the applied force, and that is takes place along the direction of the force. Only need to state the second law. Is it over? The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction of the force. Is it over? Say yes or no?
Yes, ma'am.
Okay. So now all of you write the next heading. Mathematical expression for Newton's second law of motion. Mathematical expression for Newton's second law of motion. You don't need to copy down this now. We are going to derive the equation. Write the next subheading. mathematical expression for Newton's second law of motion. Mathematical expression for Newton's second law of motion. So in order to derive an expression for Newton's second law, first of all, we can write an expression based on its statement. So what is Newton's second law of motion states? Newton's second law.
Rate of change of momentum is directly proportional to the applied force.
Applied force. So we know that the force is represented by F. So according to the second law, this applied force is directly proportional to what? This applied, yes, this applied force is directly proportional to
rate of change of motion.
Rate of change of momentum. It is directly proportional to rate of change of momentum. Rate of change of momentum means momentum with respect to time. So according to second law, we can write that the applied force F is directly proportional to change in momentum by time taken to that change. Rate of change of momentum means change in momentum with respect to time. We are already said that whenever we are describing or defining the velocity, velocity is the rate of change of displacement. So we represent velocity is equal to displacement by time, right? Similarly, here according to our Newton's second law, the applied force is directly proportional to rate of change of momentum. That rate indicates the time taken for that change. So the applied force F is directly proportional to change in momentum divided by time taken. Or we can write F is directly proportional to. What do you mean by change in momentum? Change in momentum.
In final momentum.
Yeah, change in momentum means that object must possess an initial momentum and final momentum. So the F is directly proportional to final momentum minus initial momentum. Final momentum minus initial momentum gives the change in momentum. Initial momentum divided by time taken. F is directly proportional to final momentum minus initial momentum divided by time taken. Now, we know that final momentum means mass into final velocity. The final momentum is equal to momentum means the P. It is the product of mass into velocity. But here we are calculating the final momentum. That is the product of mass and final velocity. That is given by M into capital V. Similarly, what is our initial momentum?
M into U.
Yes, very good. Initial momentum means mass into initial velocity. That is mass M into initial velocity is U. That is mu. Therefore, force F is directly proportional to final momentum minus initial momentum. That is mv minus mu divided by time taken. How we can represent the time?
Seconds.
T is the letter used to represent time. So it becomes F is directly proportional to. Here which term is common? mv minus mu. Which term is common? M. So we can take M outside. M into V minus U divided by T. V minus U divided by T. Are you familiar this term V minus U by T?
Yes.
What is V minus U by T represent?
Acceleration.
Very good.
Acceleration.
This acceleration. So here, V minus U divided by T is equal to acceleration. Therefore, we can write F is directly proportional to M into, instead of V minus U by T, here we can write A, acceleration. Okay. So with this, we can wind up. We can discuss the same in our next class. It's a time. The teacher is here.